So in Lecture 10, we're going to cover a couple of smaller bending topics, off-axis moments and composite beams. And they're just, I'd say, minor or small because they're sort of, just building on what we learned in last lecture about bending stress. So let's deal with off-axis moments first. So occasionally, we have a situation where we have a beam, and I'm just going to draw a rectangular beam for simplicity, and maybe it's going back that way, and it's experiencing an internal moment that is not aligned along one of the two primary centroidal axes of that cross section. So we've got the x-x axis and the y-y axis. So maybe, for example, the moment is acting about an axis like that. Now, in terms of orientation for moments that are acting not along one of the two primary axes, it's often customary to show the orientation of these moments with both the arrow indicating the moment and a vector indicating the orientation of your thumb if you're using the right hand rule, and then your fingers curl in the direction of the moment. So this moment could be represented like this is the combination of those arrows. So the linear arrow showing the direction that your thumb points when you're using your right hand, and M then curling in the direction that your fingers curl in. But in any case, sometimes we get these off-axis moments like this, and these are really easy to deal with. There's nothing tricky about them. All that you do is you decompose the moment, do a vector decomposition of that moment into components that act about your x and your normal centroidal axes, x and y centroidal axes, and then deal with them separately. So for example, if this angle in here was theta, then we'd say that we have an x component to this moment. And again, I'm using the right-hand rule for the directions here. Mx, which would be equal to what? M cos theta. And a component along the y-axis. And this is... Oops, let me make that a little bit better. So again, there's the moment, and this is my, and its value is m sine theta there. And then you just go about calculating bending stress at whatever point you're interested in from those two different moments separately, and add or subtract the result as appropriate. So rather than go through this and then take you through an example, I think we'll just go through the example, and that will show you how to deal with them. Again, they're not very complicated. You see situations like this where you have, let's say, a building material, a beam that is inclined and being loaded vertically. That creates an off-axis moment. This could be a member of, let's say, the roof of a building, right? You get a situation where you'd have an off-axis moment there. So these off-axis moments do occur, but they're not seen that frequently. So let's, without further ado, let's do an example with an off-axis moment and see how that comes together. So example, so we'll do a rectangular beam here, and there it is, and we'll have it coming out sort of that way there. Okay, and let's say we've got this beam is going to experience an internal moment that is oriented 30 degrees from vertical. So we've got a moment here like this where this angle is 30 degrees. And this is going to be a wooden beam, so it's going to be made of white pine. So beam made of white pine. And if you look in your material property table for a second, there we go. You will see that for white pine, there are two values. One's for white pine green, so that's when it's freshly cut, and the other's for 12% moisture, so that's standard sort of moisture content of dry wood. So this is going to be the dry white pine, so the 12% moisture. So let's go back to our problem here. So white pine, and this is dry white pine. All right, and let's give our beam some dimensions here. So 200 millimeters on the bottom, and then the height of the beam we will say is 250 millimeters. And then the question that we'll ask ourselves is, what is the maximum allowable value of this moment before failure of the wood occurs? Right? So maximum value of M before failure. Okay, so that's the question. All right, so what we're going to do is whenever you get an off-axis moment, you know, just do your vector decomposition and think about the effects of the x and y components separately. So let's just sketch that beam again, and I'll just sketch the cross section in 2D like that. And we've got our centroid and our horizontal centroidal axis, the x-axis, and our vertical axis, the y-axis. So decomposing M here, we're going to get a component of the moment about the x-axis. So here's mx. And let's think about that first for a moment. So mx in that direction, and actually I will put the rest of the beam there. In that orientation, mx is taking the top of the beam and pulling it outwards, and taking the bottom of the beam and pressing it inwards. So we've got tensile stress at the top there and compressive stress at the bottom. And the tensile stress increases within the cross section as we move away from the neutral axis of bending upwards. Tensile stress increases. So maximum tensile stress from mx will be along the top edge here. So this is maximum tensile stress from mx along the top edge. And then again, the compressive stress will increase moving away from the neutral axis of bending downwards, so that the bottom edge here is experiencing maximum compressive stress from mx. Okay. So if we're thinking about failure, we obviously want to think about where stress is maximum. So that's why we're doing this. And now let's look at the contribution from my. So the y component of that moment. So we've got my acting around that way. So for MY, the maximum tensile stress is going to be along this left-hand edge. Okay. So again, just considering MY, the level of tensile stress is increasing, moving away from the neutral axis of bending until we get to the maximum tensile stress on the edge from MY. So 0 along the neutral axis of bending for MY and increasing as we move outwards. Compressive stress doing the opposite. So 0 along the neutral axis of bending and then compressive stress increasing as we move outwards so that the location of maximum compressive stress from MY is this edge over here. So if we look at this corner here, at that corner we've got the tensile stress from the maximum tensile stress from MX adding to the maximum tensile stress from MY. The tensile stress from both of those components of the moment are maximum at that corner. Right? So we've got sigma tension max at that corner where those tensile stresses are adding. And then at the bottom corner here, we've got the same for compression. So the maximum compressive stresses from both of those components are adding together to produce the point where we have the overall maximum compressive stress. Okay, so the route in terms of how we go about calculating what the maximum tensile stress is simply just taking the tensile stress from MX at this location and the tensile stress from MY at that location and simply adding them together. And the same for compressive stress. We just calculate what the compressive stress from MX is at this location and the compressive stress from MY is, and we add them together. So that's what we'll do. But out of those two locations, let's think about which one is likely to be the location where failure will occur at. These other corners, by the way, here we have, in this case, tensile stress from MX and compressive stress from MY. So if you wanted to calculate what the net stress was at this corner, you'd need to subtract those two stresses from one another, and the same for this corner right there. So let's flip back to the material property table for a second here. And what we want is, you'll see in the table here, we've got a bunch of values. So we've got modulus of elasticity, then we've got ultimate strength parallel to the grain of the wood. The grain of the wood refers to the fiber direction in the wood. And boards are usually cut parallel to the length of trees, and fibers grow longitudinally along the length of trees. So in boards, the grain direction or the fiber direction is parallel to the length of the board. And that means in most cases that our normal stresses are parallel to the grain. So these are the values that we end up wanting. Okay, and we do have values of ultimate strength perpendicular to the grain of the wood. And it's no surprise really that these values are significantly smaller than the values parallel to the grain of the wood. Right? If you're pulling fibers apart from one another, that's much easier to do than if you're breaking fibers in tension. Okay, so let's look at the values of white pine then. So for the dry white pine, we've got a tensile ultimate strength of 59 megapascals and a compressive ultimate strength of 33.1 megapascals. So almost twice as strong as in tension than in compression. So thinking about our beam, then we just return to here. Because we've got a symmetric object, a rectangular beam, the maximum tensile stress in one corner will be equal in magnitude to the maximum compressive strength or compressive stress in the other corner, because of course when we do the stress calculation using my over I, the distance y to this point is the same as the distance y down to the bottom, and the same for if we're doing the component of the stress relative to the y-axis or due to the y component of the moment. That distance there is the same as that distance there. So because the actual stress levels in those corners that are maximum tension and maximum compression are equal, then compressive failure will occur prior to tensile failure because the strength of the wood in compression is smaller, right? So the wood will experience compressive failure first when our internal moment M increases. Okay, so we need to use our value of the ultimate strength in compression. So 33.1 the value, I think was, 33.1 there. So let's pop that, 33.1 MPa. Okay, so what we'll do now is we'll calculate what the stress is at that lower corner for both components. Okay, so I'm going to just copy this here and go over and we'll paste this over here so we have all our dimensions. We know that the point that we're interested in here is sigma comp max, right? And we know that we're breaking this moment up into an x component and a y component. Okay. Great, and let's label our centroidal axes. So this is the x-axis, and this is the y-axis there. So we're going to say that the stress, the maximum compressive stress at the location that's indicated there is going to be the stress at that location due to mx and the stress at that location due to my, and then we're just going to expand each of those. So the stress at that location due to mx is going to be the component mx multiplied by the distance that that point is away from the x-axis. So I'll call that variable y here. So this is distance y divided by Ixx plus then the stress at that location from my is the y component multiplied by the distance that that point is away from the y-axis. So that distance here, call that distance x. So multiplied by x here and divided by Iyy. And then we're setting this all equal to the ultimate strength for the wood. All right, so let's put in some numbers here, and then we can just calculate what the answer is. So it's sort of like a one-step deal here. Now, recognizing that we'll probably need some space, we'll just move this down slightly. Like this, and then do the equation on this line over here. So we'll start over here. So 33.1 times 10 to the 6 pascals, that was the ultimate strength of the wood, equals mx. So we just want the x component, so that's going to be m multiplied by sine 30, and then our distance y, which is half of the height of the cross section, height of the section was 250 millimeters, so we've got 250 divided by 2, that's 125. Change that to meters, divided by IXX, so 1/12 base height cubed. Remember, the base is the dimension that is parallel to the centroidal axis that you're dealing with. So the base in this case is the 200 millimeter dimension, and then we've got 250 for the height. Cube that, and then add on the second term here, which is my, the y component, which is m cosine 30, multiplied by the distance that our point of interest is away from the y-axis, so that's that distance right there, 100 millimeters divided by 1/12, and in this case the base is the 250 mil dimension, and now the height is the 200 millimeter dimension. Cube that. And out from that pops what the maximum moment can be before failure occurs. So that comes out to be 43.5 kilonewton meters. Okay, so that's all there is to it when you talk about off-axis moments. All right, so now we'll switch gears here and do composite beams. So composite beams. Okay, two separate topics, off-axis moments and composite beams. Of course, you could have a composite beam that was experiencing an off-axis moment, but these are two separate topics that we're covering today. Composite beams. So if we just look at a rectangular beam here, there we go, a rectangular beam that is experiencing an internal moment about its horizontal centroidal axis. That's not a very good perspective for that moment for my drawing, so I'll draw it like that. There, yeah. We know that bending stress, sigma, is my over I. And for a rectangle, I has the term h cubed in it. So our normal stress is proportional to 1 over h cubed in this case, where our height is this dimension there. What this means is that if you can increase the height of a cross-section by a small bit, then you dramatically decrease the maximum stress because height is cubed. So the idea behind composite beams is how can we increase the moment of inertia of the cross-section, primarily the height, by moving material away from the axis of bending, but not adding a significant amount of material to the cross-section. So what we want to do is we want to take this cross-section here that is made of some sort of, let's say, strong, probably heavy material, and we divide that material in two and move it away from the centroidal axis. So here's the centroidal axis, and what we want to do is take half of the material in that cross-section and put it up here, and we want to take the other half and put it down there, so that we end up with a cross-section that has a much greater height, and therefore stress will be reduced significantly. Now, of course, we can't just move these together and have them floating in space, so we need some sort of material to keep them separated. And this tends to be a material that is lightweight and relatively weak. And the job of this filler material is just to separate spatially the strong material from the axis of bending. So again, here's our internal moment. So here we've got material on the top and the bottom that is strong and heavy, right? Probably expensive. And we've got material in the middle here that is weak and light and probably cheap. So the composite beams are used all the time for different things. You know, if you think about a pair of skis that or a surfboard that might have fiberglass over foam, or you think about a beam in a building that is maybe wood with steel plates on the top and bottom, or a mast for a high performance yacht that might be carbon fiber around a foam core, etc., etc. So a really good way of adding strength without weight. So the question is, how do we deal with composite beams mathematically in terms of figuring out the stress? And the way we do this is by using what's called a transformation method. So in order to calculate stress in a composite beam, we imagine transforming that composite beam to an equivalent beam made of only a single material. Okay, so I'll show you what I'm talking about on the next page here. So we'll just grab this drawing here and flip over and paste it back here. Okay. So we take this beam that we have as a composite beam, and what we say is that we're going to leave the strong, heavy material alone. Okay, so I'll redraw that. Okay, there we go. And what we want to do is take the light, weak filler material that's inside here, that's only job is to space out the strong, heavy material from the axis of bending, and we're going to replace it by a piece of the strong, heavy material that would deform in the same manner as the weak, light material. So if that filler material was to be the stronger material, then it could be much smaller and do the same mechanical job. So we'd replace it by a piece of material that looks like this. Has the same height as the original piece, but has a greatly reduced width. So if this dimension here is the original width of the beam, W0, then this dimension here is the transformed width, W subscript T. So transform into beam made of only strong material. Okay. All right, so we want to do that transformation so that the deformation of that central material will be the same when a moment is applied, or when the material experiences an internal moment. So we can figure out what that relationship has to be. Okay, so if we look at how this cross section is going to deform under that moment, and maybe we'll just draw a longitudinal view here to help us out. So let's draw longitudinal cross-sectional cut through this composite beam here. So we'd have something like this, and then our moment is acting around in that direction, M. We know that the material at the top of the cross-section is going to be pulled out in tension, so we have a tensile strain here, and then at the bottom of the cross-section we have an equal and opposite compressive strain. So there's our compressive strain, and we have a linear transition between those two where we've got zero strain at the neutral axis. Now, an important point is that for composite beams to work effectively, the filler material and the high strength material need to be bonded securely together, so there can't be any slip at that interface there. So this interface there, for composite beams to work correctly, there can't be any slip. No slip. Well bonded for composite beam to work effectively. And that's because if you think about what's happening down in this cross-sectional or the longitudinal view of that cross-section here, we've got the full cross-section is rotating about the common centroidal axis of bending that's in the center. If the high-strength material on the top and the bottom aren't well bonded to the filler material, then both of those pieces of high-strength material are just going to rotate about their own centroidal cross-sections instead of the centroidal cross-section of the whole combined cross-section, which is going to defeat the purpose of the composite beam, and it's going to be equivalent to the situation that we started with, where we had no filler material in there and greatly reduced height. Okay, so getting back to what we're getting at with this longitudinal drawing. Here, the maximum strain that's seen by the filler material is this strain right here, right? So that we'll call that strain the original strain in the filler material E0. When we transform the beam, we have to size that center piece of material that we're replacing the beam by with a piece of material sized so that we have that exact same strain profile over the cross section. So in other words, we need to have the cross-section changed so that this tensile strain remains the same value, this compressive strain remains the same value, and there's the transition between here so that the strain that would have been experienced by the filler material is the same when the strain is transformed. So we want to have in these two drawings epsilon naught is equal to epsilon t. So the original strain in the filler is equal to the strain at the same location in the transformed material. So let's work a little bit with this equation on the next page here. So we've got epsilon naught equals epsilon t. We know that for materials under the yield stress, Hooke's law gives us the linear relationship between stress and strain if our material is linear elastic. So we can substitute in stress here. So we've got the stress at that location in the untransformed material divided by its modulus of elasticity has to be equal to the stress in the transformed material at that same location divided by the material for the transformed beam. Now what we can do is we can expand those equations out. So basically what we're looking for again is we're saying, okay, well, we've got a piece of filler material that's like this. It's experiencing an internal moment m, and we want it to deform equivalently to a very thin piece of different material that experiences the same moment m. And importantly, we haven't changed the height of these, or at least if the moment was about the y-axis, we wouldn't have changed the base. So you want to preserve the dimension here that is perpendicular to the axis of bending and just change the dimension that is parallel to the axis of bending. So this is W naught, this is WT. Okay. So for the stress in the original filler material, that's given by our bending stress equation. We have my over I for that original untransformed material, and then we're dividing by the modulus of elasticity there. And for the transformed beam, we've got the stress, and remember, we're considering the stress at the same location here, that location there. So we've got the moment, which is the same, internal moment. We've got distance y, which is the same for both of those, because we're considering the same location. I for the transformed material, and then modulus of elasticity for the transformed material. So we've got cancellations of m and y's on the top here, and we have 1 over I naught E naught, 1 over IT ET. Okay. So now what we can do, considering that these are both rectangles, we can substitute in what the equation for the moment of inertia of each of those two shapes above here is. So we've got 1/12 the base for the untransformed filler material was W naught. So we've got W naught, and the height is h, and we cube that, and then we've got modulus of elasticity E naught, and 1 over 1/12 the base length of our transform material is WT, and h cubed, and ET. And then we can again cancel off the 12ths and the h cubes. So what we've got now is an equation that tells us how big the transformed material needs to be so it will deform equivalently to the untransformed material. Right? All we have to do is take the original width and multiply it by the ratio of the moduli of elasticity of those two different materials, and we'll get an equivalent width for a beam that would deform in the same way when loaded. So that enables us to actually do stress calculations then. If now we can produce a beam that's an equivalent beam that's just made out of one material, we can calculate its modulus of elasticity, we can calculate stress. But when we go to calculate stress of stresses in our transformed beam of part of the beam that wasn't transformed, right? So for our transformed beam, we have a picture in our example here that looks like an I-beam, right, where the center portion is the transformed material. If we want the stress in the untransformed material, then we can simply use our equation my over I, and I is for this transformed beam, and that will give us what the stress was in that original untransformed composite beam. Okay, there we go. So the stress that we calculate from this equation here gives us what the stress is at that same location in the untransformed beam. When we want the stresses in the material that was transformed, so let's say we want the stress somewhere in here, right, in the filler material. In our transformed beam, we look at the equivalent location and we can calculate the stress there using sigma equals my over I. But when we want to take that back to what the stress was in the filler, we need to multiply again by the ratio of the moduli of elasticity to get what the stress was in that filler. And I can show you why that's the case. That's easy. We just have to return over here and we take this little bit of the expression out, copy that, and paste that back in, right? And this tells us that the stress in the original material will be equal to E naught over ET multiplied by the stress in the transformed material. And the stress in the transformed material, actually I'll do this on a new line so I can put a box around it a little bit more easily. So the stress in the original material, E naught over ET, and then the stress in the transformed material would be given by my over I transformed. Okay. So this gives us the stress anywhere in the material that we've transformed in our transformed beam. Okay, so let's just write a summary of what we do for composite beams. For composite beams, how to handle them. So first of all, one, we transform the beam into a beam of only one material. Into beam of one material. Okay, two, we calculate the dimensions for the transformed beam. So a new width dimension if we're dealing with moments that are occurring about the horizontal centroidal axis. So calculate transformed dimensions. Oops. So that's using our equation. The transformed width is the original width multiplied by the ratio of the moduli of elasticity, right? EO over ET there. And then what we do is we calculate the moment of inertia for the full cross-section of the transformed beam. Calculate I trans, right, moment of inertia for the transformed cross-section. Okay, and then once we've done that, then we can calculate stress. So for stresses, oops, let's try that again. For stresses in the untransformed material, we simply use sigma equals my over I for our transformed beam. And then for stresses in the transformed material, we do the same thing, but we just have to remember to multiply the result by the ratio of the modulus of elasticity of the two materials. So my over I transformed. Okay. So let's do an example problem to show you how this all works, because that will make the whole process make a bit more sense. So example. So in this case, we're going to have a piece of wood that is topped with a piece of steel to increase its strength. So we've got something that looks like this. We've got a steel plate like this, and we'll assume that it's probably bolted to a piece of wood below. All right, so this here is going to be 304 stainless steel, and it is going to have a thickness of 50 millimeters. The whole width of the beam is going to be 175 millimeters, and then the other material is going to be Douglas fir. Douglas fir wood. Okay, and then the height of the wood here is going to be 200 millimeters. Okay. And then we're going to say that this beam is experiencing, so here's the centroid, and we're going to say that the beam is experiencing a maximum internal moment, or it will experience a maximum internal moment, which we found out probably from a moment diagram, of 15 kilonewton meters. And it's going to be in that direction, which is placing the steel in compression and the bottom of the wood in tension. And what we want to know is, for this maximum moment, what is the safety factor for the steel and the wood? So for a max of 15 kilonewton meters, what is safety factor of the steel and the wood? Okay. So let's think about this. In order to calculate the safety factor for either the wood or the steel, what we're going to be wanting to do is take the ultimate strength and divide it by what the maximum stress currently in the wood is, or in the steel is, in the material is. So that's going to be for the wood. And then for the safety factor for the steel, we want to do the same thing but with yield stress. So we want to do that. So this is for wood, and this is for steel. So we want the maximum stress in the steel and in the wood. All right, so composite beams, the way to deal with those is to transform them, but before we do any transformation here, we should retrieve the material properties for those two materials from the table so that we've got them ready. So let's go figure out what the modulus of elasticity is for the wood and the modulus of elasticity is for the steel. All right, 304 stainless steel here, and we're on the metric side. Modulus of elasticity 193 gigapascals. So 193 gigapascals there. And for the wood, we've got Douglas fir. Here's Douglas fir, 13.4 gigapascals there. 13.4 GPa. Okay, so we'll transform the Douglas fir into an equivalent piece of steel. So we don't touch the stainless steel, right? We leave that alone for our transformed beam. There it is. And we say, okay, if the Douglas fir was steel, we could have a much smaller piece of steel that would do the same mechanical job. So our beam would end up looking like this. And again, the moments acting about the horizontal centroidal axis. So we do not want to change any of the dimensions that are perpendicular to that axis. So this dimension here that was originally 200 millimeters, that dimension needs to stay as 200 millimeters. But the width gets reduced significantly. So we can figure out what WT is by taking the original modulus of elasticity over the modulus of elasticity for a transformed material and multiplying it by the original width. So the modulus of elasticity of the original material, right? That's the wood being transformed into the steel. So the wood's the original material, and that has a modulus of elasticity of 13.4. And we're doing a ratio of moduli here, so I'm going to leave them both in gigapascals, so the units cancel. And then the modulus of elasticity, ET, that's the modulus of elasticity of the transformed material. So we've transformed that into steel. So ET is 193 here. And then we multiply by our original dimension of 175, right? And that gives us what the equivalent sized piece of steel that would deform in the same way. And that comes out to 12.15 millimeters. Okay, there we go. So now what we want to do is calculate the moment of inertia of that transformed cross section. So I'm going to throw on a couple of dimensions here and then paste this to a new page and take it with us. So we've got WT sorted out there, so it's 12.15 millimeters, and this dimension across the top was 175 millimeters. Okay, so let's steal this here, and we'll take that to a new page. There we go. Don't need that up here. Okay. The first thing that we need to do for figuring out what the moment of inertia is of this shape it's a T section, so we can't do regular superposition with moments of inertia and rectangles to figure it out. We're going to need to use the parallel axis theorem, which means that we need to first know what the location of the centroid is here, y bar. So we want to figure out what y bar is first. So the equation, sum of a y bar over sum of a for the component shapes that make up this cross section. So dealing with the top piece of the T first, we've got an area of, and I'll just do this all in millimeters, 175 millimeters multiplied by 50, and then y bar, so we want y bar just for that top piece up here, and it's located, centroid is up there. So that's going to be what, 225. So we've got 225 there. And then we add on the same quantity for the upright piece of the T. So its area is 200 by, let's just shift this over a bit so we don't run out of real estate. 200 by 12.15, sorry. And then its centroid is located 100 millimeters from our datum at the base, so 100. And then we're dividing by the summation of the areas. So 175, 50 plus 200, 12.15. Okay. Equals, what do we get for that? 197.83 millimeters. All right, so now we're in the position where we can calculate the moment of inertia of this transformed cross-section using the parallel axis theorem, I plus AD squared. It's supposed to be an A in there. So let's do that. For the top piece in blue, we have its moment of inertia about its horizontal centroidal axis. So we've got 1/12. Its base is 175 millimeters. I'm switching to meters now. Its height is 50 millimeters. Cube that. Add back on its area, 175, 50 mils. And our quantity d squared, don't forget, is the distance between the centroid of the shape that we're considering and the overall centroid. So that's going to be our value of y bar that was right up here, subtract the value of y bar for the whole cross section. So we've got 0.225 minus 0.1973, and then we square that term. And then we add on the same thing for the upright piece of the T. So 1/12, the base, 0.01215, the height, 0.2, cube that. Add back on the areas, 0.01215, 0.2, and then again, distance d is between the centroid of that component shape and the centroid for the overall cross section, which is right there. So that distance is going to be what? Given by the centroid for the whole cross section, subtract the centroid for that piece. 0.19783, subtract 0.1, don't forget to square it. Okay, so that gives us I for our transformed beam. So that's 3.96 times 10 to the minus 5 units of meters to the 4th power. All right, so now we're in a position where we can start looking at calculating strength, or safety factor. So if we deal with the steel first, we know where the steel is going to experience maximum stress. So moving from the centroidal axis here up to the very top. That's where the steel is going to experience the maximum stress. So on our transformed cross section, that is, again, right up at the top. And that piece of steel hasn't been transformed. So we're dealing with the untransformed material, which means we can calculate the stress, the maximum stress in the steel, just using our equation my over I transformed. So let's flip back here and say that for the steel, our safety factor is given by the yield strength of the steel divided by the maximum stress in the steel, which is the yield strength in the steel, divided by my over I transformed, right? Okay, and this is the maximum value of y down there. Okay, so let's put in some numbers there. So the yield strength of 304 stainless steel. Let's go back to the material property table here. 304 stainless steel, yield strength 207 megapascals. So we'll pop that in. 207 times 10 to the 6. Right, and then we'll put I for our transformed beam up top. We've got 3.96 times 10 to the minus 5, and that's in meters, and then divided by m and y. So m was given to us in the problem statement. That's 15 kilonewton meters, so 15 times 10 to the 3 to put it into units of newtons and meters, and then our distance y. So I'll just flip back to the other page for a second here. So we're going all the way from the neutral axis of bending to the farthest point in the steel that we can go. So that's going to be given to us by what? This is the overall centroid location. So if we take the whole height of the beam, which is 250, and then subtract the centroid location, y bar, then we get that value of y max. So we've got 250 here, 0.25, subtract our value of y bar, which is that guy there, 197.83. Okay, so pop that in and do the math on that. And what do we get out of the other end? We get out a safety factor of 10.4. So that's for the steel. For the wood. Okay. For the wood, the situation's a little bit more complicated, and it just requires a little bit of extra thought, and that's because if we look at the material property table, there are those differences in strength between the tensile strength and the compressive strength of the wood. So the wood is weaker in compression than it is in tension, or it's stronger in tension than it is in compression. So looking back at our diagram here, we know that our maximum tensile stress in the wood is going to occur at the bottom here of the cross section. The maximum compressive stress in the wood is going to occur right here at the top of the wood before the steel. Now, the compressive stress is going to be lower than the tensile stress, or the maximum compressive stress is going to be less than the maximum tensile stress, because the distance from our axis of bending to the location of maximum compressive stress is smaller than the distance from the neutral axis of bending to our location of maximum tensile stress. but the wood's also stronger in tension than it is in compression. So that's where we have to weigh things out. In this case, it's not really too much to think about, because we know that Y bar has a value of what, 100, and it was 197 millimeters, right? So this centroid location is almost at the interface between the steel and wood, because this dimension is only 200 millimeters. So this value of Y here, going from the neutral axis of bending to the farthest point away in the wood that would experience compression, that distance can only be a maximum of about 3 millimeters, which means that the compressive stress is going to be really tiny. So even though the compressive strength of wood is less, we can safely assume that the wood is going to fail in tension, and just look at the point of maximum tensile stress. Okay, so looking at tensile failure for the wood. So here we go. And considering tensile failure, what we want to do is say that the safety factor is going to be equal to the ultimate strength for the wood in tension divided by the maximum tensile stress that occurs. So we've got sigma u tension divided by my, again y max, over I for the transformed beam. And here's the spot where we have to think about or remember the fact that we're calculating the stress in the material that was transformed. So we had wood, then we went to steel when we did the transformed beam. So consequently, this stress here has to be multiplied by the ratio of the moduli of elasticity for the two materials, like this. Okay, so let's put in some numbers on that. The ultimate strength of the wood in tension was 33.1 megapascals, so 33.1 times 10 to the 6 there. And then let's just check that that's correct. Is that correct? 33 point, no, that was for white pine, right? That was for the last problem that we were doing. So the correct value, good thing we checked, is, nope, we don't want compression, we want tension, is 85 megapascals. So let's go back here. Erase this off. 85 times 10 to the 6 divided by the ratio of the moduli of elasticity. So that was 13.4 gigapascals divided by 200 and 193 gigapascals. Again, let's just check those numbers to make sure we had them right. So yeah, 13.4 and 193. Then our moment, so we had 15 times 10 to the 3 for 15 kilonewton meters. Our distance y, so that's the distance from the centroidal axis here, from the centroidal axis down to this point where we're going to experience maximum stress. So from the centroidal axis down to the point where we're going to experience maximum stress in the wood. So that's the value of y bar here. So that's 197.83. All divided by I for the transformed beam. So here we've got 3.96 times 10 to the minus 5. Okay, so do that calculation and we'll get 16.3 out. All right, so hopefully that helped you with how to actually approach those problems that involve composite beams. And there's a few others in the textbook if you want to do a couple of more examples or look at them. So those are available to you as well. And don't forget that the solution manual for that textbook is freely available online. So you've got nice handwritten solutions for each of those problems too. Okay, so I'll leave it at that for today, and we'll see you again for lecture number 11.